Hi, Luke.
Hey, yeah, how are you?
I'm good. Do you want to try and share?
What's that?
Do you want to try and share just to see if it's working?
Sure. Just give me a second. Sorry, I'm slowly waking up.
How are you feeling?
I'm good. I wonder if
Was it tough?
it was fine. It was lingering, but I was definitely not up for a talk last week. Let me see here. And I ended up postponing some of the talks too. Let me see.
Turns out he wasn't very wise, huh?
I mean, I suspect Fabrice must have the number, but I suspect 30% of the attendees. Do you see my screen?
Yeah, I see it.
It's in presenter mode.
Yeah, it looks good.
Okay. I'll just leave it like that, so you don't have to see my face in full zoom. Yeah, I think, I mean, Luigi got it. And I mean, you saw the email, right? You're on the wide mailing list. So
yeah,
French style, you just leave the name.
It was hard for me to tune in because of the time zone. So I could only see a couple of talks, but I was getting the updates by email. So
yeah, we're getting, it's like, no, it's, yeah. I've been fine. It's just, it was lingering.
And was it towards the end that you started to feel?
Yeah, it's on my flight home.
Okay.
So I didn't get stuck over there because at the time you still had to give a negative test. Jim Thompson, same situation. He tested 24 hours, before flying back, like me, and he arrived in at UW, same thing. All his students got it. Everybody got it.
Yeah. Oh well, I'm glad everyone is okay.
Yeah, so far so good. I was worried about Luigi, but he emailed me right away. And Evan, Alex, I mean, some of them looked pretty bad. They were fine. I think they got the special antiviral medicine. But yeah, no, I definitely felt it.
Yeah, a lot of folks that I know are also have it right now. So
yeah, I mean,
it seems like now it's a time. Everyone, like I'm still Invicto, so let's see.
Yeah, I mean, for me, the issue is really the I mean, it's this brain fog thing, like focusing and stuff. Last week was hard. And yesterday was my first full day back in the office.
Yeah,
I felt it. So
the thing is that I haven't been sick at all for 2 years. So I think whatever I get, it's gonna feel terrible.
Well, no, that's what I regretted. I was like, oh, maybe I should have got it like right after my booster. Time is it?
It's 2 minutes.
That's good. Ernesto, Tom. Oh no, Jacob.
Right, I'm just going to give it a minute, Luke. Folks are still tuning in. All right, so good morning, everyone. Welcome to the Odyssey webinar series. On behalf of the science team, it's a pleasure to welcome Luc Lenain, who is going to talk about wind, waves, and currents. And please take it away, Luc.
Great. Well, thanks, Bia. Can you hear me okay?
Yes.
Good. So this is a very informal talk. So please, if you have any questions, feel free to interrupt. The goal here is really to provide a description of the kind of capability the air-sea interaction laboratory has developed here at Scripps in terms of remotely, remote sensing observation of surface wind, wave, and current from meso to submesoscale and smaller. This is obviously very relevant for this project, and I hope you'll find some interest in what I'll be presenting. It's going to be a bit of a potpourri of various programs and various experiments that we conducted with different focus. So again, please interrupt me if you have any questions. To set the stage a little bit, one of the things that I always like to remind everybody is having this kind of a general conceptual picture of the process of Earth interaction. We know that the ocean and the atmosphere exchange mass, momentum, and energy, regulating Earth's weather and climate. There are complex processes, in great part because, as you can tell, I'm not going to go into details of each one of those processes here. There is a complex interaction across a broad range of space and time scale. And obviously, all those processes need to be better understood and in turn, better parameterized to constrain coupled RC model. So traditionally, we've been doing a very good job with in situ observation, temporal information, but spatial observation is a remaining challenge. And that's what I'll be talking about mostly today in the context of new instrumentation and new measurement capabilities that we've been developing here. And in particular, that really enables us to develop better physical understanding of wave current interaction processes. So today, again, this is going to be a potpourri of different projects. I'll be talking about observation, high resolution observation of surface wind, surface current, and directional properties of surface wave collected from several experiments. I mentioned the TFO ONR funded program in May 2021, where we flew across two small counter rotating eddies separated by 100 kilometers. So we expect to see quite some interesting wave current interaction. And S-mode that all of you by now are familiar with. And I'll also mention some work that we did on SWOT, including with BIA, which I think is important to put in the context. You know, this is the idea behind this airborne instrumentation package is to collect a broad range of type of observation, and I'll go into that at the beginning of the presentation. So I'll be talking about the MASS. This is the instrument, the modular aerial sensing system. The DOVIS is one sub-instrument as part of the MASS, and it's been bringing a lot of interest in terms of the measurement that we can obtain of surface currents and you know, very you know, upper ocean vertical shear as well. I'll demonstrate you know, the need to have those kind of higher resolution current observation. For example, when you compare to operational model that do not include some mesoscale physics in it, and talk a little bit about wave current interaction across multiple scales. A lot of this work is very preliminary. The instrument itself is fairly new, though I'll be talking about some older results as well from the MASS. So to get things started, I'll spend a bit of time talking about the MASS. I think it's important for this community to understand the broad range of capability of this instrument. The MASS instrument is not new. You know, we started under the leadership of Ken Melville, who was the head of the lab at the time, about, I would say, 12 years ago. We were initially funded through NSF. So one of the NSF MRI, American Recovery Act type project to put together a system to provide better observation of ocean surface processes. And I'll go into details of the instrumentation. A few years later, ONR wanted one too and funded a second one for other application. So in the end, we've had a lot of use from this instrument, over 720 hours of accumulated flight time with, I think, 25 different field campaigns now. We operate it from a variety of aircraft, small helicopter, nice comfortable jets like the NASA G5 and various platform. Fundamentally, with what we're talking about, you know, we collect sea surface, you know, we provide characterization of sea surface displacement of a broad range of scale, temperature, ocean color, surface kinematics, along with, you know, ocean wave, directional wave properties, Stokes drift, sea surface height. I mean, everything is written here. With actually quite a bit of hydrological and terrestrial application, which in turn for us, it's a lot easier to characterize fixed target. And so we've done a lot of work for snow cover, coastal geomorphology, El Nino, sea level rise kind of impact, also working with local stakeholders for decision making. I've shown this plot many times for some of you guys, but I really like this image here, and I'll get to that in a second. The MASS is really built around a scanning waveform LiDAR. This is a Regal Q680i. It provides observation of surface wave, surface slope, and directional wave spectra with great accuracy. So this is an example here of a color-coded georeference point cloud. This was collected on some of our first real experiment back in 2011 in the Gulf of Mexico. Wind speed was about 12 meters per second, 3 meters significant wave height, with about 25 centimeter spatial resolution. And we're flying all around this buoy that happened to be called, and I found out later, the Luc platform. And what I like to show here is those color points here, those outliers. They're actually not outliers. They're birds flying around the buoy which I think give you a pretty good understanding of the kind of resolution that you can get. So the uniqueness of the mass is that it doesn't only have a LiDAR. We also have a suite of electro-optical systems, infrared camera in the long wave IR range. We have a number of high resolution video camera. We have hyperspectral camera. All those optical systems give us information about ocean surface processes. We can get wave kinematics, wave breaking statistics. We have information about temperature fronts, et cetera, along with biochemical information, ocean, through the ocean color, and everything is coupled to a GPS IMU. I'll spend some time focusing today on a new instrument called DOPVIS that is part of the MAS that enables observation of surface current, vertical shear, and wave breaking statistics. And the surface current here is computed through dispersion relationship, kind of looking at the spatial temporal evolution of the waves, of the wave field over a certain period of time. I'll start with that because, I mean, this is some work we did with BIA not too long ago. But one thing you can do with a LiDAR, if you, instead of looking at some of the small scale processes, you can do cross-track average and do very, very long transect. And this is important for a number of projects, including SWAT. So one of the things that we're able to do is to start looking at, to start collecting observation of broadband, to collect broadband observation of sea surface height from the mass. And this is a paper that it's not submitted anymore. It's in GRL, and I encourage you to look at this, where we try to describe different regimes in the slope of your SSH spectrum associated with different processes. We are, and I'll talk to you about that in a second. Well, this is actually how it looks like. Again, if you fly over a very long distance like this, this is one leg here, you can start computing SSH from mass. This is compared to Sentinel-3 product. You can look at the significant wave height, and you see very good agreement between the two time series, at least at those scales. And this is some work that we'll pursue as part of the SWAT program. We'll be flying the mass to support the CALVAL once the satellite is launched in orbit. The other thing I was going to say is that the 3D point cloud that I mentioned, if you fly into one direction, this is a swath of data here about 350 meter wide and about 6 kilometers long. You can take this swath of data, you can compute a spectra out of this. And this is the kind of things that you get, directional spectra down to very high resolution. We're able to achieve roughly kilometer down to sub-meter directional resolution in your spectra. There's some very interesting properties in the directional spreading, going from bimodal to unimodal direction that we've looked at in this paper here. We can azimuthally integrate the spectra and start also looking at the different regimes that we expect, with different input balancing each other out, depending on whether you're on the equilibrium range or the saturation range. So again, this is some things that we looked in detail. So very precise observation of the surface wave, from some meter all the way to 100 kilometer kind of wavelength, which is one of the strengths of the system. Another things that we did, and this is described in more detail in the paper below. This was with SCAN and Xdatum. One thing you can, because it's a LiDAR system, you can actually start looking at the number of, your distribution of returns as a function of angle. It's a scanning system. And it gives you some information effectively if you assume specular reflection about the mean square slope. So we're able to compute mean square slope that way. So this is not based on the surface elevation from the wave. This is really enables us to get to much higher, shorter wave content, if you like. And we're able to do that, and we can actually invert for wind speed. So now we are actually able, and I'll show some other example, to not only measure surface wave elevation, but we can measure mean square slope, and in turn we can infer the wind. So here I'm showing some data of wind speed computed from the mass. It's in red. This is the same long flight that I mentioned that we did as part of SWAT. And in black, it's the Sentinel-3 product, which was collocated in space and time as much as possible in ECMWF kind of product. And obviously, ECMWF misses some of the shorter scale submesoscale kind of variability, but you find a very good agreement between, considering very good agreement between Sentinel-3 and the mass. And again, to me, this reinforces the need to really collect those high resolution with measurements as part of those, if we want to get better understanding of the relation between this current wind wave system. This is another example here. We like to fly over a certain amount of time for different tracks to look at the spatial temporal evolution. I mentioned we measure SST, and I'll go in more details later on with this. So this is multiple tracks, about 2.5 hours of data, I believe, something like this. Upwind, downwind of SST, crosswind, we measure SSH. I don't know if I even showed it here, but the thing I wanted to mention is, over 2.5 hours, we're able to capture the spatial temporal evolution of the wind speed over one of those swaths here. So switching gear a little bit. So there's been a lot of work on this, and it's been published in the literature. Hang on one second. One of the things that we added during the pandemic, really, we developed this instrument. Not completely new. The concept is, has been discussed for many years now. Going back to Duggan et al. and all the teams that have put it together. But the idea is quite simple. We installed a very high resolution camera looking forward of the aircraft track, and we do very straight lines. So what's going to happen is that if you have a very wide angle camera, this is kind of an image, a georeference image that you get from this camera, and you can see up to several kilometers away. And if you have a lot of images like this, you can start looking at the same spot of the water for extended period of time. If you capture the spatial temporal variability of surface waves, then you're going to pick up the dispersion relationship, and you can actually invert for current and then actually get some depth information, because different frequencies and wave number will have different penetration depth. And that's what we do. The idea is really simple. The implementation is really complex because of calibration, because any kind of error in your motion compensation is going to mess up your inversion completely. So I'm going to show you how it looks like. If you look at the image here, so it's going to be a movie. It's twice the speed, so I think it's about 1 minute of data total. I added an aircraft in the image just so that you know where the aircraft is. This is not part of the image, and I'll show you a little bit what it looks like. So you see all those braking happening, and those little squares are the location where I can start looking at 3D FFT to invert the current. So I'll play it again. You can see a lot of details. You can see multiple wave braking actually all over the place. You see the evolution of the wave. So we have, typically at least 20 to 30 seconds of data within one spot. So I mentioned wave braking. For people interested in braking statistics, it really enables us to track breakers over a much longer period of time, and including looking at breakers, shorter wave breaking on top of longer wave at roughly the same locations. So that's something that we're looking at with a student here at Scripps. These are contour breaking wave that we collect from DubViz. So very, very rich data set. And it's the fact that you have the ability to kind of pick and choose where you collect the data makes things a lot easier. People that are doing observation of braking statistics knows that sun glitter is a bit of a problem. So that's been really helpful in that sense. Anyway, going back to surface currents, we take those data, we do a 3D FFT to obtain a 3D spectra, and this is what we get. This is some work that we're doing with Ben Smeltzer and Simon Elixon. Ben did his PhD on this topic in laboratory observation. We're using the same kind of tools that we have. And at this point, ultimately, the goal is to develop the ability to get vertical shear information. But at this stage, we're just going to be focusing for this presentation. I'm just doing depth average current for simplicity with different resolution. I'll start with 1 kilometer and I'll go to higher resolution for S-mode. So the first experiment I'm going to talk about is called TFO. It's a platform-centric ASW processing with through the sensor data assimilation and fusion. This is funded through ONR. And the ultimate goal here was to combine PIs with an acoustic background, physical oceanography background, and RC interaction to acquire collocated observation of all the themes so that we can better understand and predict acoustic propagation. So what I'll be focusing on here is some flights that we conducted as part of the experiment with the twin otter and the mass of Southern California. What happened is that at some point, the conditions were too rough to redeploy the acoustics. So we were left with about, I think, 5 or 6 days of ship time. And in very high wind conditions, 4 meter C, 30 knot winds. So with the physical oceanographers on the ship, we created this experiment of opportunity, quote unquote, targeting counter-rotating mesoscale eddies that were apparent in an ICOM simulation of the eye, which is right here. So again, in the context of DOPVIS being able to measure surface currents, it was a great opportunity for us to validate how well ICOM was representing the location of those eddies and comparing some of the surface currents, high resolution ICOM product with actual observation. And this is what we did. So what I'm showing here, color coded in the background is SSH from ICOM. The vector field in red is the surface current at the higher resolution available at the time of the measurements, and in black is the observation from DOPVIS. And you can see that, generally speaking, we can see that the low, the large scale kind of behavior is similar between the two products, but clearly there is, there is some things missing, some mesoscale variability in particular. So if you look at a transect like this, and you compare the east and north components of the current, disregard the blue line, it's really the red line is ICOM, black line is the mass. We see again that we're capturing fairly well. Here, there's definitely some things missing. The general larger scale behavior, mesoscale behavior, if you'd like, of the current, but clearly we're missing a lot. And it's, if you look at different transects, like there's all those small scale variabilities that are actually consistent. And one of the things that I should mention is that systematically we do reciprocal passes with the mass. So for example, here, this is another transect, again, compared to ICOM. So the black one is going on a northern kind of heading, and the gray one is coming back on a southern heading. And you can see that qualitatively, we see the same kind of small scale behavior in both those passes, which is quite remarkable. And you'll see that it's not always the case when you have inertial current, and I think I'll show this with S mode, where there's definitely some variability associated with temporal variability. So one of the things that I did, for example, for this flight here is, I took the same current, and this time I cranked up the resolution. So we have about 250 meter resolution here. I should mention that every single of those quiver vector is computed independently from one another, meaning that there is no smoothing, no averaging, this is what you get. And that's why sometimes there is some outliers. See this big vector here. I just decided to leave it because it also gives you some idea. Those features are not something associated with any smoothing part. But anyway, this part here seemed interesting. You see a lot of variability in the eastern in the east currents here, a lot of wiggles at few kilometer scales, and there is a sharp change of temperature. What I'm showing here is a temperature in the background. So if you zoom in again from here, you see a sharp SST front. You see strong modulation of the current that is measured independently from the same platform but different instrument, and those beautiful kind of smaller scales, some mesoscale variability in surface current, which I think is quite remarkable. I'm showing here on the right the same data, but this time as a time series. So you see a front here, this front over here corresponds to this front over here, this front over there is over here, and you see kind of like this jet-like very rapid change of current, of up to 0.25 meter per second over the course of less than it's pretty much 250 meters. So very, very strong shear happening here, which is quite nice. Along with the temperature, along with the current observation, we have measurement of surface wave. I mentioned that earlier, and this is something that we're hoping to push with BIA. You can start looking at observation of significant wave height. This is 2.5 kilometer product, and the first things that you see is, and again, this is all reciprocal passes. So there is, these are not temporarily evolving features over the course of the flight. The spatial variabilities that you see here remain over several hours. But what you see is that you get spatial variability in the order of 20% from one leg to another. It's about 80 kilometers to go from here to here. So it's quite significant. I'll note that for each one of those points, not only we have information about the bulk properties of the wave, but we get the directional spectra and omnidirectional spectra, as I mentioned earlier, along with the winds as well. So you can you can really break down the physical processes that will have an impact on the modulation of surface wave in two. You're going to get wave refraction, and Fabrice and Lionel and Bia has been looking at this, and local effect, which is associated with wave current interaction at much smaller scales. I'll show this quickly. This is some work that Bia did with some data that we collected. Oh, sorry, my phone is ringing. From those SWAT flight that I showed earlier. Bia ran a simulation using different, forcing a wave stream model with different current estimate, numerical current estimates that are shown here, globe current and case, which is the current from the California State Estimate. So this is a control without any current. This is with different type of current, and what you're showing here is what you're seeing here is the modulation of significant wave height is better represented with the model with current as compared to no current. And obviously there is still some differences, but it's going in the right direction. So that's some things that it's really calling to get much better, high resolution current for this kind of measurements. And this is something we're hoping to do, like run simulation with BIA over this 280 system, so we can start looking at the role of this 280 system, which should be very interesting in focusing the energy in various places in the operation, in the up area. Another thing that we've been exploring is the role of small scale variability in the current in modulating surface wave. This is again what I showed earlier, where we had this front over here. And what I did here is I computed a spectral saturation for like a mean saturation. So this is over a very short wave. This is a compensated integrated wave spectrum, if you'd like, which is used in, typically in wave studies, including by Lionel Romero. And one of the things, so this is the things that I want to show you here. So this is SST current. So there is change of currents over here in east and north component. Remember, the waves are going in that direction. So the important current is going to be the one going to the north or to the south. So that's really this one over here. And what happened, if you look at this variation of mean saturation, kind of look like the shape of the north current. And effectively, if you looked at it a little bit in details, is that you have reduction of saturation when the wave and the currents are in the same direction and large, and that's what we're seeing here. And in gray, there's low current and waves are going in the same direction. So this is consistent with at least what we expect out of this. So that's for the TFO program. I'll spend a bit of time on S-mode because a number of you are very familiar with the program. It's kind of like the overview of S-mode, characterizing the contribution of submesoscale ocean dynamics to vertical exchange of climate and biological variable in the upper ocean. It's, to develop a better understanding of those processes, we're collecting a combination of in situ and airborne remote sensing observation. And we conducted a pilot program back in May 2021. And I just wanted to give you a hint. I mean, this is what I was showing you here is really nice, but some people will say, well, like maybe it's just an artifact of the measurements. So one of the things that we did during the pilot program, sorry, it takes a little bit of time, is to start looking at grid. This is a 1 kilometer product surface current from Dobbs. And you see this very nice consistency from one pass to another. We also had in situ observation from wave gliders to start comparing those surface currents with in situ observation, and it's in the work with the student here, Hugo. So a lot of things happening. But the thing to me that was remarkable for me is the very energetic submesoscale variabilities that you see at the location of the site. Again, we have information about the wind speed collocated, so we have currents and wind speed. Sorry, it's not exactly the same size. We do see a lot of spatial variability in addition to temporal variability in the wind speed condition computed from the mass. I mentioned we measure waves as well, but I'll skip through that. This is another example here. On another day, we're flying in the morning, and you see this jet-like kind of features on the left side of the plot with current rotating here. And this is the afternoon, so you can see a significant temporal variability in just a few hours, which is not unexpected. I'll skip through that. I guess we have the waves again. This is bulk observation of the wave. I'll focus more on that. So we collected a number of flights. We collected data during a number of flights during S-mode. And this is the SST product. We have a pencil beam SST product that gives us information about the larger scale variability in temperature on different days here, different locations where we were operating. And it's really useful to start looking at some of the smaller processes. And this is, then you can start combining SST and surface current, for example. This was on the 4th and the 5th of November. And one of the things that I'll point out here, I don't know if you notice, there's a rapid change in the current magnitude here associated with the front, kind of similar to what I was showing with TFO. So we looked at it a little more. We have higher resolution product as well. for the camera and for Doppler, for surface currents. We're actually able to get 128 meter spatial resolution for the current. So this is this area over here, blew up a little bit. The color represents the sea surface temperature. You can see actually, I don't know if you can tell, but there is a surface signature of line circulation kind of aligned with the wind. The wind was coming from the west. The vector field here is from Doppler, and because it's a vector field, you can start looking at gradients. So this is a gradient in the vertical direction, dVdx, and you can actually also look at average shear, which can't really tell here from the plot, but some of the steps here that you see correspond to step in the shear that we're finding from the step in the temperature. Sorry, correspond to steps in the current shear. So a lot of things to look at. Oh yeah, and surface signature of Langmuir cell. So today was really an opportunity for just showing the kind of capabilities that our group has been bringing forward in trying to better observe those very difficult processes. These are not trivial, as all the SMO team know, like this is very difficult observation to collect. So this was really a potpourri of capabilities that I think are going to become very relevant for Odysseus. Ultimately, if anything, for Calval processes, the same way we're providing support to SWAT, there is going to be a need for validating the kind of observation that such system would collect. And in addition, we need to better understand what is the spatial temporal variability of surface wind and surface currents, so that we can really drive set of requirement, in putting together an orbital system like this. So I hope it was not too much. I just thought it was important to at least give you a breadth of the range of things we can do with the mass. Thank you.
Thank you very much, Luc. That was wonderful. Let's thank Luc both virtually. All right, so we're open to questions now. Real quick, Martin asked if the HICOM simulation had tides, and I think that is just the 112 analysis product, right, Luc?
I have to double check, but I think it had tide. I'm pretty sure it had tides, actually.
I doubt it. If you got it from hicom.org, there's no tides.
I have to double check. This was from Bruce.
He gets it from that, Luc, but anyways,
Okay.
let's check it.
Yeah.
Sorry, I'm trying to, someone has their hand raised and I can't see who that is.
Okay, I'll just make one comment though about HICOM to Brian. The trick here is that from an AV standpoint, they use those operational model, for example, to define the location of an experiment. And one of the things that happened for us for TFO, the team followed HICOM and said, okay, we're going to go over there because this is an area where there is not too much current, so it's not going to drift too far away. We went over there, and all the array just like went crazy. There was a lot of current. We could see it from our wave gliders. So it's also reminders that while a operational model can capture mesoscale features, there's still going to be some submesoscale features that are not captured and parameterized that can wreak havoc in your experimental planning. And that was kind of the things that that was important there.
Yeah, that makes sense. I think HICOM doesn't resolve the submesoscale well, that's for sure.
Yeah, but it's nice to see it. I mean, we know it, we expect it, the physics is not there, but it's nice to be able to show it.
Dudley has his hand up. You can go ahead and unmute.
Hi, Luc. Thanks for the nice presentation. Towards the end there, you showed several examples of gridded maps of surface velocity. Could you go back to the first of those? Most of those look very consistent to me, but my eye has a tendency to look for inconsistencies.
Yeah, that's good. Yeah.
Bad habit. But but keep going back to the very first one of those. Feels back a little more. So that looks good there. That looks good. This is the one. Yeah, I think this is the first one. This one, something concerns me there. If you look at the middle two rows there, and you look at about 123.8 west longitude.
Yeah.
Those adjacent rows there, the vectors are perpendicular to each other. And I mean, I find these maps to be very exciting because I'm very interested in the vorticity and divergence and stuff. But that looks a little peculiar to me. What do you make of that?
Inertial motion. And so that's the trick with when you look at, so they're not, like, we didn't collect them necessarily like one after the other, going north, for example, but we did reciprocal passes. And what we find, and I thought I had the plots in here and I can send them to you, because we have reciprocal passes, within 40 minutes, you can see significant changes in current in the order of 0.2 to 0.3 meter per second. So this is inertial motion.
It's also a change in direction.
Yeah.
Yeah. Okay. Well, that's the only map that I noticed that in, though. So I'm not sure why it would be particular to that one, but in any case.
It has to do with the temporal difference because this takes, it takes 4 hours to map all this.
Yeah. Okay. Thank you.
Yeah.
Luc, Fabrice asked if you could talk a little bit more about how DOPVIS works.
Sure. In what way, Fabrice?
The fact that it's similar to HFR.
Yeah, basically the principle of the measurement, what is that we're actually measuring in terms of velocity?
Yeah, I thought
I think you said it, or maybe I don't, yeah.
Yeah, I mentioned, that's the same thing that I was talking about at Ifremer. The idea is very simple, and it's similar to expand system, for example. You take you're able, this is a stack of imagery at the same location. So it's in georeference frames. The aircraft is flying at 180 miles per hour, but we georeference it very carefully. So the image is stabilized. And we take the stack of data and we just do a 3D FFT. And then we invert, we obtain, these are slice spectrum. We obtain a KX, KY, omega 3D spectrum, and we fit in 3D space a dispersion relationship for each wave number increment. So in the end, what we obtain is the current as a function of wave number.
Right. So look, I have a question about that. So if we're thinking now about a spaceborne instrument and just in the context of Odyssey, if let's say DOPVIS would be the way to do CALVAL for that instrument, for example, how would you, because you said you're looking at depth average currents. So how, like at which depth would you compare the measurements to the satellite measurements?
Well, that's something we're going through with Doppler scat. What are the depth measurements that Doppler scat is collecting? We have a pretty good idea for depth range. The higher the frequency, at which you're computing the current, the closer you are to the surface. There is some question mark on the shape of the current profile that you need to assume. And to be able to translate frequency into depth, and that's a research question that a grad student or group is going to be tackling, working with NTNU, because it's still not clear, despite some of the work from Jeff Campana and Ben on all of this. I think S-mode is going to be very valuable in better understanding, what a Doppler scat-like instrument is measuring as compared to DOPVIS, where we can constrain the depth range. If that makes sense.
Yeah. Are there more questions? Well, I have another question. Look, we've talked about this before, but just for the sake of the community, could you touch on like whether or not there is a Stokes drift in the measurements from DOPVIS?
There is no Stokes drift in DOPVIS. And I forget to repeat it every time. And I think that's the strength of it. That's, you know, it's the beauty. I mean, the physics behind it is really simple. The implementation is much harder because you have to be able to georeference a very high resolution product, and obviously computationally it's extremely heavy. I mean, as you can imagine, that's a challenge here. So, and that's why it's also going back, and I don't know if Ernesto has anything to, if Ernesto is still on the line, I guess not.
Yeah, I'm on the line.
Oh, okay. Like, I mean, that's, you know, that's like the exciting part of like working together with Ernesto in trying to better understand, you know, Doppler scats measurements.
Yeah, and I think that the data that you've shown are incredible. And to me, that they become the gold standard of what surface currents at a few meters are. And I think the velocity shear question is something that we really need to use either S-mode or other campaigns to really make the case for Odyssey in the long term.
Yeah.
That's an issue that we need to understand.
Any more questions for Luc?
Luc, this is Roger. Just clarifying again the method that you use for DOPVIS. So then you fit one dispersion relation and you get estimates of the current average to different depths effectively based on the wave number along the dispersion relationship. Is that correct?
Yeah, so I get a current per bins of wave number, yes.
Okay, great, thank you.
So, and there is subtleties because, so if I increase, if I look at high resolution products, like this, which is 128 meters, then I don't have a lot of, I cannot resolve the very long wave number, so I can't resolve the larger depths. So if I want to resolve the larger depths, I have to get larger cubes of data, but then there is, you know, less temporal information. So there's a lot of subtleties in the way you're processing the data, but it's designed, you know, you parameterize it based on your objective, whether you're looking at, you know, want to do vertical shear or horizontal shear.
Luc, how does the performance would depend on the wind speed? What if there is no winds or no waves?
So like so far, and we don't have enough data to really look at it. I mean, obviously, if you have no waves, you're in trouble. The challenge is going to be if you, like, this is designed to, so the DOPVIS is designed to really fly at low altitude because of all the other instrumentation. LiDAR, we can't fly super high. So we really focus on the shorter waves. So it definitely works better with shorter waves. But on those flights, for example, during S mode, it was mostly driven by swell. And it worked out really nicely as well. So again, this is, you know, we really did two big experiments with DOPVIS. We had actually quite a range of condition, and so far it's been working really well. And a lot of our, you know, characterization on working really well is based on self-consistency, you know, with reciprocal passes, with looking at the variability of the current as a function of wave number. You know, how high of a frequency can we resolve? I mean, this inversion, you know, feeding this dispersion relationship is not trivial. There's a lot of subtleties about it. So this is more what we're doing. However, now we're in a position for S mode where we have collocated observation under the flight of the aircraft with upward looking at ECP. it's not the same thing. This time you're going to get Stokes drift. This time you're going to get some pseudo-Lagrangian drift associated with the way we're measuring things. But we're hoping to start looking into that in the coming weeks, actually, now that the data are processed.
Jacob, would you like to ask your question?
Please question here.
Okay, it's fine. Luke, do you see Jacob's question?
In the letter, yes. To separate a geostrophic component from the Dove's total velocity. It's something to look at. I mean, I think it's in principle. I mean, you should be able to get geostrophic velocity from at least the lower range of sea surface height that we collect from the mass. But we're also looking at the transition between unbalanced and balanced motion with Mara Freilich, who is a postdoc here at Scripps, and she's been looking at some of those data in the context of you can obviously, oops, it doesn't work anymore. If you take If you take those kind of time series of surface velocity, you can start looking at kinetic energy and looking at kinetic energy density spectra. So that's some of the things that she's looking at now, and see if we can capture this transition between those two regimes.
Luc, could you comment on, because I think once you mentioned that you can actually get a small swath for Doppvis. So how wide would that be? And if you compare the flat altitude, because for mass also you get like a 500 up to 500 meters. So is there a way to?
So it's about, at 1,500 feet, it's about 750 meter swaths for Doppvis. And the way we process it is not necessarily the smartest way at this point, because I just use cubes not in the direction of the flight, so it's just in UTM. So there's room for improvement. It works well for S mode because we were roughly aligned in the north and east direction. But then when we fly, so like those data here at the very end are 3,000 feet data. So we get about, I believe, 2 kilometers at least. Well, at least, I mean, you're seeing here 8, so 1.2. So there's more. I was zooming in here. So about 2 kilometers swath.
There are more questions for Luc? Mark has a question for you, Luc.
Try EEMD rather than an FFT. I actually don't know what EEMD is.
Mode separation, but in atmospheric.
Oh, I see what you mean.
Showing
Yeah.
better
I haven't.
distinction of the spectrum.
Yeah,
So,
no, I have not. That's a good idea, actually.
All right, so if there are no more questions, then let's thank Luc again for this wonderful talk. Next week, we're gonna hear from Alex Weintier, and I hope to see all of you there. Mark or Tom or Narso, are there any announcements?
Not that I know of.
No announcements? Okay, so thank you, everyone. I'll see you all next week. Thanks, Luc.
Thank you.